Okay, so we're going to finish chapter 28 today, though the university has said that Tuesday is pretend Monday. That wasn't on the schedule at the beginning, so I'm not really planning on us meeting on Tuesday. Okay? Now, your final exam is written, it's printed, it's 250 points. It's 250 questions long. No, it is 50 questions long, but they come in clumps, like fill in the blank in glycolysis, for example, and there's several in a row, and so it's not as many as you think. There's also some synthesis questions with multiple steps, fill in the blank, and sort of several items in a row. So it's not as long as it sounds. I think when you see it, you will feel like it mostly focuses on the latter half of the class, but you'll also find some stuff from earlier portions. All right, so I don't know why I told you that other than that now you can panic about it, but it was coming whether or not you were worried about it. So it will be given in the testing center. Pay attention when the testing center is open and hours and such. All right, we're talking about transition metals in carbon-carbon bond forming reactions. And I was trying to show you how you can assign metal oxidation state. And also, because this is going to be helpful in understanding what's going on when we talk about the reactions involving these metals. Assigning oxidation state for a metal is easier than you think. First, you have to realize that the organometallic chemists and the inorganic chemists don't bother with formal charge on atoms in the complex. But they do have to show you what the overall charge on the complex is. If you know the overall charge on the complex and you know the difference between an L-type ligand, which is neutral, and an X-type ligand, which is negatively charged, assigning oxidation state is easy. For example, here, I know that the complex has overall charge of +3. I know that each of these ligands, ammonia, is an L-type ligand. You assume that the electrons in the bond between the metal and the ligand belong to the ligand. And then you say, if the ligand leaves, does it leave neutral or negatively charged? For these ammonia ligands, of course, NH3 with a lone pair leaves neutral, which means that this +3 charge must be from the metal and not from any of the ligands. You got it? If the ligands were negatively charged, we would adjust the charge on the metal to match the charge on the overall complex. So in this case, all of the charge must be, because of these neutral L-type ligands, all of the charge is on the metal, which tells you that the metal is in the +3 oxidation state. If the metal were a 0 oxidation state, it would be neutral, right? +3, another way to write that is cobalt 3. Now, we won't talk about this, but if you ever take an inorganic chemistry class, they'll tell you that different metal oxidation states have different stabilities, and so some oxidation states are more stable than others. Along the way, in addition to assigning oxidation state, it's useful to know how many electrons the metal has. So we call this the D electron count. This can tell you whether the metal is electron rich versus electron poor. To identify the D electron count, you have to know the number of valence electrons that usually come with the metal. So for cobalt, that's 9. 9 valence electrons, but we're going to minus 3, that's the charge. 3 electrons are missing, that's why it's +3. So we conclude there are 6 D electrons on the metal. That can be useful later on when predicting the spectroscopic properties of a metal. We won't do that in this class, but it can also be useful in figuring out whether there's space for more things to be attached to the metal. And then, so the two things you need to know how to do are assign oxidation state for a metal and figure out how many d electrons are on the metal. Another interesting feature is the overall electron count. Recall that for for second row elements, we've sort of had this octet rule, no more than 8 electrons around carbon, right? And that's how we got really uncomfortable with the Texas carbon. Metals have more orbitals available to them, the d orbitals, for example, so there's more spaces for electrons to go. If you count in this complex, you have 6 pairs of electrons, 2, 4, 6, 8, 10, 12. 12 electrons from the ligands shared with the metal. And then you have 6 d electrons for an overall electron count of 18. This is an 18 electron complex. And we would call that, I don't know, coordinatively saturated. That's the new octet rule for transition metals, no more than 18 electrons. Yeah.
So is it equally uncomfortable to add another one to this as it would be to add a 5th to carbon?
Is it equally uncomfortable to add something else to bond to cobalt as it would to carbon? I think so. Yeah. So, for example, you would say, if I changed, maybe you'd make some predictions here, and again, this is outside my area of expertise, but if I changed the cobalt oxidation state, suppose I reduced it to cobalt 1, so that it had 8 d electrons, you'd think at least one ligand would have to leave, so we don't max out on the 18 electron count. Okay. Questions about assigning metal oxidation state? Maybe we better do a couple other examples, but yeah.
So what's the difference between d electrons and electrons from the ligands?
The d electrons versus electrons from the ligands? Yeah. The d electrons are the valence electrons that are held on the metal, and then the electrons from the ligands, yeah, come with the ligands and leave when they leave. So, but between the two, your limit is 18. So that can, if you know the d electron count, then you have a feel for how many ligands you can attach to the metal. And this can help you understand what mechanistic steps are reasonable.
So when you're counting those electrons from ligands at 12, were you just counting the bonds?
Yeah.
To NH3?
2, 4, 6, 8, 10, 12.
And would one of those in each of those bonds be a d electron?
No, that's the thing. So we're counting the bonds involving the ligands. Those electrons belong to, come from the ligand.
Okay.
Yeah.
And where are the d electrons?
They're on the, we could draw a bunch of lone pairs on the cobalt, but we won't.
Okay, so they're lone pairs.
They're implied, yeah. All right, good. What else? Yeah.
Just want to make sure I understand this right. So the 6 d electrons, that's because we look at the periodic table, we say that cobalt should have 9.
That's right.
Subtract these 6 because it's at +3.
That's right. Yep. Right. So getting to that conclusion requires you to know the charge on the complex and that all of these are neutral L-type ligands. Yeah. Okay. Yeah.
How do we know the charge? Will it usually just say?
Yeah, it has to show you. Yeah. Yep. This is unlike those early questions in 351. Assign the formal charge on. No, like they have to tell you. All right. Good. Others? Okay, let's do a couple other examples of transition metal complexes. Here is a cuprate complex involving, well, let's just say what these groups are. 1, 2, 3, 4, 1, 2, 3, 4. Good. This is a cuprate complex, and the overall charge is 1 minus. So let's first figure out what the ligands are. We have 2 basically R minus. These are X-type ligands. If this 4-carbon chain left with its electrons, it would be negatively charged, right? 1, 2, 3, 4. Okay, so the overall charge is, let's see, overall charge is minus, 1 minus. Oxidation state, you've got 1 minus, but then you have to account for the fact that you've got 2 X-type ligands. So I'm going to take the charge on the complex, or -1, and I'm going to subtract the overall charge from the ligands, which is -2. And that gets me an overall oxidation state of +1, or in other words, copper 1. If you come up with a number like 2.5, you've done something wrong. There's no half charges, half oxidation states. Okay, let's do d electron count, except we can't spell. So, number of valence electrons that usually come with copper. Copper's electron rich, normally comes with 11. But the oxidation state is 1. So we have 10 d electrons. This is a d10 complex. Or in other words, it's electron rich and the d orbital block is full on this copper. All right. And then let's do overall electron count. By the way, you can sometimes use the d electron count to determine whether a particular complex is going to be paramagnetic. That is it going to have unpaired electrons? We won't worry about that here. Overall electron count from the ligands, we have 4, right? These 2 pairs of electrons, 4 from the R- ligands, and then we have 10 from 10 d electrons. Overall 14 electron complex. Okay. I think that's good enough. We could, maybe one more. Let's do palladium bonded to a phenyl group, which I can draw. Triphenylphosphine. Another triphenylphosphine. A bromo. And then this one's weird. And this one's kind of hard to draw. What we mean by what I'm going to draw here is that the pi electrons from the double bond are coordinating the metal. So I can't actually, I don't want to draw a solid line because I might communicate that I got more electrons than I actually do. But how do I show the pi electrons coordinating the metal? That's about as good as you can do. All right, and the overall charge on the complex is 0. So let's identify the types of ligands. Triphenylphosphine is an L-type ligand. It leaves neutral. The pi bond is also an L-type ligand. It leaves neutral. Br is an X-type ligand. It's negatively charged. And then this benzene ring is also an X-type ligand. If it left with these electrons in that bond, it would be negatively charged. So, for our overall oxidation state, we're gonna take the charge on the complex, which is 0, and we're gonna subtract from that any of the charged ligands. So we have 2 X-type ligands minus 2. Overall, this is a +2 oxidation state. This is palladium 2. Now we can determine how many d electrons palladium has by coming up here, looking at the table, and let's see, palladium has 10 valence electrons. D electron count, 10 valence electrons, but we got to subtract 2 from oxidation state to give us 8 d electrons, okay? And then total electron count in the complex is 8 d electrons plus 2, 4, 6, 8, 10 from the ligands. That's 18 overall. Okay. Notice we're not yet talking, nor will we, about complex geometry. It's a different world here. We've got predicting what the geometry of the metal should be isn't as easy as it is with valence shell electron pair repulsion. There's different geometries that are available to metals. We're simply not worrying about them. Mostly because I don't understand. I'm an organic chemist. What do you want? Okay, so, exam 4 key. That would be fun to look at. Not funny, yeah. Listen, there is a price, but it's a lot higher than $5. Just kidding. Not for any amount of money would I disclose that. Okay, so we talked about this reaction last time, a carbon-carbon bond forming reaction. I want to illustrate the mechanism now, and we're going to use what we've learned so far about d electrons and oxidation state to sort of follow along. So this is a cuprate. What we do now is going to be similar to what we did up here. This is a copper in its +1 oxidation state. You can tell it's +1 because the overall charge on the complex, I used to write it as a formal charge on the copper. Now we'll be a little bit more sophisticated and just write it as an overall charge on the complex. We'll get rid of the lithium counter ion there. So this is copper 1, and again it's got 10 d electrons. So let's show you the mechanism of the reaction. I told you it was not SN2. One thing about reaction mechanisms involving transition metals is a lot of times they don't push arrows anymore, they just show intermediates, which is always irritating to me, and you can choose to push arrows if you want. We'll take a lone pair on the copper, and we will have copper attack the Sp2 hybridized carbon at the same time as we have bromine move and attack the copper. That looks like something that doesn't make a whole lot of sense. Never seen anything like that before. I'm going to try to draw a transition state, and it may or may not help. The transition state involves copper and let's see, 3, 4, 5. Oops, we're going to put a dotted line here for a new bond forming between copper and the Sp2 hybridized carbon of your vinyl halide. We'll show a dotted line here to indicate the breaking bond between copper and bromine, and there showing the new bond forming between copper and bromine. And still, overall, the charge on this complex is 1 minus. And this is the double dagger indicates that this is the transition state for that reaction. I'm going to just move all this down to the, it doesn't matter for our purposes, but when I export this as a PDF, it hates it when I cross the page border. All right, so this is the transition state. Sort of a 3-membered ring transition state, not unlike what you saw before with, say, the MCPBA reaction with an alkene or bromination. Only it's the 3 atoms involved are copper, the sp2 hybridized carbon, and then the bromine. Let's look at the product of that first step, and then we're going to have a particular name for that kind of step. Okay? After that process, and the charge is still -1. Okay. Now, let's assign oxidation state and do a d electron count and an overall number of electrons in the complex. All right. Overall charge is -1, but we've got 1, 2, 3, 4 X-type ligands, right? The 3 pH phenyl group minus is one of the ligand, or 2 of the ligands. We've got 2 of those. We have 1 of these, and we have 1 of these. And it doesn't matter that these electrons originally in the bond between copper and the carbon originally came from copper. They now belong to carbon. So for oxidation state, we've got to subtract -3, and we 4 helps to be able to count. And we come up with the +3 oxidation state. This is copper 3. All right, so that's an oxidation step as far as copper is concerned. And what's that oxidation step? It's called, well, it involves 2 electrons that used to be on copper, now belonging to one of the ligands. I should say you can't actually tell which electrons come from copper and whether they end up in the copper-carbon bond or the copper-bromine bond. Can't tell, and it actually doesn't matter. But this step, because it involves addition of these 2 atoms to copper, and because copper gets oxidized, we call this oxidative addition, and it is one of the fundamental steps that organometallic complexes do. Okay. We could also do a d electron count. This is +3 oxidation state. Copper normally has 11. So 11 -3, or D8. And that's another way you can tell that it was an oxidative addition, because we went from something that was D10 to something that's D8. Overall, total electron count, you've got 8 from copper, and then you have 2, 4, 6, 8 from the ligands. So that's a 16 electron count. All right. And that sort of confirms that, yes, indeed, there was space around the metal for this kind of oxidative addition step, because we're still below our limit of 18. All right. Now, overall, we're going to make a new bond between carbon of the alkene, the sp2 hybridized carbon of the vinyl bromide, and then the carbon from one of the ligands on the cuprate. How does that happen? Well, at this stage, we could push arrows like this. You're not really going to like it. We can have electrons from one of the phenyl ligands move over to make a new carbon bond, and then these electrons go back on the copper. That's one of the ways for drawing the arrows. The transition state would look something like this. It's going to actually look very similar to this transition state. You've got copper, bromide. This copper alkene bond is breaking, so we're going to have a double bond there. At the same time, we're making a new bond between copper and the benzene ring of the phenyl group at the same time as we're breaking the bond between copper and the benzene ring of the phenyl group. Again, this is a transition state. You got three things happening. This is the new bond that we make. These are the two bonds that we're breaking. And then afterwards, when the reaction's done, you've got the product, and then you have copper down to one phenyl group and one bromo group. We could repeat the analysis, but we would conclude that this is copper 1. You've again got 10 d electrons. In making the new bond between the sp2 hybridized carbon of the phenyl group and the sp2 of the alkene, copper gets 2 electrons back. We go back from d8 to something that's d10. This is called reductive elimination. So this is sort of the reverse of oxidative addition. It gives us our new carbon-carbon bond, but it returns copper to the original oxidation state. All right. Questions about that mechanism? These aren't SN2-like steps. Don't worry about, oh, well, is the copper attacking the anti-bonding orbital? It's more complicated than that. Just understand that the copper is involved in the chemistry. The chemistry doesn't happen without the metal. So that's an example of what we call a cuprate coupling reaction. But it's a nice way to demonstrate, first, making a type of carbon-carbon bond that we simply couldn't make before, and then also to demonstrate the idea of oxidative addition and reductive elimination as key mechanistic steps in these organometallic reactions. All right, questions? All right. So there's 3 more reactions to learn, and they are all Nobel Prize winning reactions. So the first is a Nobel Prize that was shared by 3 scientists. We'll talk about 2 of the reactions, and then we'll do the second in a little bit. The first is called the Suzuki reaction. And the Suzuki reaction is actually like perhaps the world's most useful synthetic reaction, used like crazy in the pharmaceutical industry, because it's essentially a Lego type reaction. You can click together diverse pieces that have similar functional groups, so it allows you to mix and match to generate a lot of different types of molecules. You need on one side an aryl halide. And this can be a bromide or an iodide. I'm not sure about chloride, and we'll keep pretty close to the types of examples in the book. And then you need either a vinyl or an aryl boronic acid or ester. So I'm going to show you an example of a Suzuki reaction, then I'll show you some other things that work. This is a boron, and if you have two OH groups attached, this is a vinyl boronic acid. That's the name of the functional group with the boron and the two oxygens in the one R group, a boronic acid. Kind of like a carboxylic acid if this were a carbon and that was a doubly bonded oxygen. The catalyst for the reaction, and this is one of the reasons it is so useful, is that you only need a small amount of catalyst, is palladium with 4 triphenylphosphine ligands. That's a neutral palladium 0. I will say this reaction works so well that it's been an active area of research to see whether or not you can get it to go without the palladium. And so occasionally over the past, 5 to 10 years, you'll see papers in the literature that'll say, ooh, a palladium-free Suzuki reaction. Except that when people go to reproduce it, it doesn't work. And the reason their palladium-free Suzuki reaction worked is because they had trace amounts of palladium in their glassware. Like, it's so reactive that you don't need it's such a good reaction, you hardly need any palladium at all. But even trace palladium counts. You can't call it palladium-free. All right, the new bond that you form is a coupling reaction between the sp2 hybridized carbon of the aryl halide and the sp2 hybridized carbon of the boronic acid. The stereochemistry of the alkene is preserved. Okay, and that gives you your product. All right, so you've got there are a lot of aryl halides that are commercially available. You can have any number of things attached to this benzene ring, other things, a lot of different functional groups. You could have any number of things attached to the alkene, and the cross-coupling reaction works. That's called wide substrate scope. A reaction that can tolerate a lot of other functional groups but still works is a really, really useful reaction because you don't have to try to reinvent the wheel. So let me show you the catalytic cycle, or what happens. Often the catalyst that you put into the reaction is not necessarily the active catalyst. It often has to do something to begin with. So let's look at this tetrakis triphenylphosphine palladium complex. We said before the overall charge is 0, so with that in mind and the fact that you have 4 L-type ligands, you would conclude that this is palladium in its 0 oxidation state. If we go to our periodic table, we can see that palladium has 10 valence electrons. So this is a D10 metal, and the total electron count is 18. All right, 2, 4, 6, 8 plus 10. Now, that tells you that that complex is coordinatively saturated. There's not a lot that can be done there. There's no space. So that's a clue that this is not your active catalyst. If you wanted to do an oxidative addition step, you got too many electrons surrounding the palladium. So what has to happen first, before anything can happen, you've got something called ligand dissociation. This is sort of the boring SN1 sort of version of transition metal ligand chemistry. You go from having 4 ligands surrounding the metal to having only 2 ligands surrounding the metal. So we lose 2 triphenylphosphine groups. They're still around in solution. They're still available for things, but they've got to fall off before the complex can do anything. All right. So then I'm going to let's just draw the actually, it doesn't matter. You can keep drawing it that way. I'm just, for convenience, want to have the phosphine ligands over here. All right, so here's your aryl halide. The first step is an oxidative addition step. As with before, or transition metal chemists do not push arrows this way. I'm going to do it just so you can sort of follow along. I'm not going to draw the transition state. It's very similar to what we saw for this oxidative addition step up here. We get a new bond between the benzene ring and palladium, and a new bond between palladium and the halide. Overall, the charge on the complex is 0, but we have 2 X-type ligands, so palladium must be +2. We're counting each of these electrons as though they belong to the ligand, even though 2 of them originally belong to palladium, and that's why we're calling it an oxidation step. Palladium, let's see, it's still D10 here, but it only has 14 electrons. Now palladium is D8, 2, 4, 6, 8, and has 16 electrons. It's important to note that this palladium-2 complex has 16 electrons because there needs to be space for what's going to happen next. Okay, any questions about that oxidative addition step? All right. Now, we have up here our vinyl boronic acid. What's going to happen here is kind of difficult to push arrows for. This is called, overall, it is called a transmetallation. The bromine here is attached to the palladium metal. The carbon here is attached to the boron metal. Boron sort of vaguely counts as a metal. And so we're going to swap ligands, or rather we're going to swap who's holding on to whom. In other words, after this step, boron is going to be attached to the bromine, whereas palladium is now going to have the vinyl group. So do you see we've sort of just swapped out who's attached to whom? If you want to push arrows for this process, you could show the electrons in the boron carbon bond attacking the palladium and bromine leaving and attacking the boron. Okay, questions about that?
Is it because bromine has spare electrons that bromine that comes across, or could it be any of them?
Why is it that the bromine exchanges over instead of any of the other ligands? I don't know, actually. That's a good question. I will say too, let's see, I think your text points out, well, never mind. That's a minor issue. Okay, so this is transmetallation, but basically if two metals are each bonded to two different ligands, the metals can swap ligands. It's called transmetallation. We won't worry about exactly what's going on other than it involves close approach of this boronic acid to the transition metal complex and a handoff. I didn't draw the transition state. We could, but I don't think it would necessarily add too much to our discussion. All right. Let's see. So the next step is reductive elimination to get us back to the palladium-2 complex. Reductive elimination is going to look like this. The electrons from the phenyl group are going to attack here, and then these electrons go back on the palladium. And because of that, we generate our new bond, and we do so in a way, as I said, that preserves the stereochemistry around about this carbon. If it was trans here, it's trans there. And then notice again, we go from this palladium-2 complex that has 8 d electrons to something that now only has, that has 10 d electrons. Okay? All right, and this step is called reductive elimination. Yeah.
Just a couple questions. So after the transmetallation, is that a reversible process at all?
Transmetallation, could it go backwards? I don't know. It's a good question. Others? All right. So let's just say a little bit about the types of vinyl or boronic acids or esters that work. Aryl halides we won't say much about because you guys know how to make those. That's a electrophilic aromatic substitution kind of question. But where do we get vinyl or boronic esters from? Here are a couple of options. You can take an organolithium reagent like this phenyllithium, and you can use this sort of weird boron reagent. Basically, what happens is the organolithium reagent attacks the empty p orbital on boron, and you get this intermediate complex with a negative charge on the boron, which loses one of the methoxy groups to become neutral. So this is a boronic, this is an aryl boronic ester, which you can use as at this stage. So if we did the Suzuki reaction involving this aryl halide and this boronic ester, that would be a way, let's see, of making a biphenyl system, two benzene rings coupled to each other. And then another option for making a boronic ester is just sort of hydroboration of making a vinyl boronic ester is hydroboration of alkynes. So hydroboration is a reaction from 351. We used BH3, but you don't have to, and it turns out that the molecule I'm drawing now is called catechol borane, but it does hydroboration in exactly the same way as BH3 does. Syn addition of boron and hydrogen across the pi bond of the alkyne. And this can then be your another reagent for the Suzuki reaction. This is also an example of a vinyl boronic ester. Okay. All right, questions about the Suzuki reaction? I think your text shows that in the Suzuki reaction, in addition to the catalytic amount of metal, you often need a base to help things go. I don't know what the purpose of that base is, and I'm fine if you forget that it's important. It likely is involved in the transmetallation step. Maybe having an extra OH group there helps with the transfer of the ligands, but I don't know. All right. So I think when we introduced this topic, sort of said, what about this weird, what if we wanted to make this sort of weird molecule with a biphenyl linkage? Oops, how could you do that? And if we're thinking backwards sort of in terms of the Suzuki reaction, one option would have been to put the halide here and then over here to have the boronic ester. And then, yeah, using Suzuki conditions, can you couple the boronic ester with the aryl halide? All right, so that's reaction number one. We got two more to go.
Is there any selectivity if we were to put the bromine on the other versus?
Could we have done it the other way? No, yeah, that would have been fine. You could mix and match. It would be maybe a decision about the ease of synthesis or what you could get. All right. Because of how useful the Suzuki reaction is, there are a ton of aryl halides and a ton of aryl or vinyl boronic esters that are commercially available. And this has really enabled drug discovery. A lot of molecules, as they were discovered, a lot of the medicinal chemistry used to make the molecules used in drug discovery has involved the Suzuki reaction. All right, that's a decent place to break, so let's pause there. When we come back, We've still got the Heck reaction. That's actually the guy's name. And then lastly, something called metathesis, which is kind of fun. So let's start back up in round 9. All right, back to the home stretch. We're almost there. A couple more reactions. So the Heck reaction is also a coupling reaction, though the substrates, and it also involves palladium. The substrates are different. One of them is anyway. You can use either a vinyl halide or an aryl halide. And then your other partner is an olefin, so you don't need a boronic ester for the Heck reaction. You can use an olefin, though your olefin, your alkene, needs to have, in general, an electron withdrawing group attached to it. So in this case, you've got an olefin with an ester attached to it, but this electron withdrawing group could be any number of other things. The conditions for the Heck reaction involve a source of palladium. This is palladium acetate. If we were to draw what this complex looks like, it would look like this. An acetate group is just the conjugate base of acetic acid. So the acetate ligands are they're interesting in the sense that you draw this complex like I'm showing you here. The acetate ligand is L-type on the carbonyl oxygen and X-type on the other oxygen. Of course, these are resonance stabilized, so you can't really tell which is which, but looking at a complex here, you can see that if the acetate ligands left, they would leave as negatively charged. The overall complex is neutral, so this is a source of palladium-2. Palladium-2 has 8 d electrons, but the total electron count on the complex is 2, 4, 6, 8, 16 electron complex. Okay, that's the source of palladium. You need a base. The base will show up in the mechanism, so we need it to help us with an elimination reaction, regenerating the catalyst, and then we need phosphine, this source of phosphine as a ligand. The phosphine ligand of choice is not just triphenylphosphine. Now we're going to add methyl groups at the ortho position. Why did they do that? I don't know. People that discover new reactions, including in the Michaelis lab, when you've got a reaction you want and you throw something in there to see if it works, one of the variables you can change to optimize things is the structure of the ligand. So in this case, they must have found in some case that adding the methyl groups made the yield better or made the reaction faster. I don't know which, and I haven't read the literature, but that's one of the areas that you can tinker when you're doing research, is what's the structure of the ligand. The new bond is between the sp2 hybridized carbon of the aryl halide and then one of the two carbons of the olefin. All right, so let's show you a little bit about reaction mechanism. I guess one thing I want to point out, it's not obvious from the aryl halide, but if we used a vinyl halide like this, and then we used some, let's use say Cn minus, and then you use these same reaction conditions. As I said, the new bond that you form is preferentially trans with respect to this double bond, but stereochemistry here of the original vinyl halide is unchanged. So let me show you, let's start with the cis vinyl halide. and then use these same conditions. Because that vinyl halide was cis, it's got to stay cis here. This double bond from the olefin is still going to be preferentially trans, but this stereochemistry from the original vinyl halide is fixed in the starting material. Okay? So you can control the stereochemical outcome of the reaction based on the stereochemistry of the vinyl halide. All right. What I mean is this double bond from the olefin is going to be preferentially trans, but the one from the vinyl halide starting material, that stereochemistry comes from the starting material and doesn't change. All right. Let's do mechanism. This mechanism is a little bit weird because it turns out that what you put in, palladium 2, is not the active catalyst. You might ask at this point, well, why not just throw in the active catalyst? Wouldn't that work better? And the answer is, I don't know, maybe they tried that and it didn't work for whatever reason. So what ends up happening is that you first bring in 2 of those phosphine ligands, and they are going to replace the 2 acetate ligands. So what would that look like? This would be palladium bonded to 2 of those phosphine ligands. Only in this case, it's palladium 2+, and it's thought that hydroxide, which I'm not sure if you add or whether it's just residual or generated from the air, but it's thought that hydroxide attacks that positively charged complex to get some weird, please do not memorize this. This is just, I went and looked this up because your text says, hey, even though you put palladium 2, that's not the active catalyst, and I kind of wanted to know where the active catalyst comes from. Again, I'm sorry for showing you all of this, but what ends up happening is one of those phosphine ligands that you add attacks the oxygen and makes a new bond with oxygen. Phosphorus-oxygen bonds are pretty strong, and those electrons go back on palladium, and that will reduce the palladium, to palladium 0. Again, that's all for your enrichment. Your text doesn't show you that. It might have been better had I not showed you that, but I wanted to sort of address the question, why don't you just throw in the same stuff as you do in the Suzuki reaction? And the answer is presumably they tried that and it didn't work as well. Also, these 2 reactions were discovered in different labs independently, and so yeah, sometimes the reason why things are chosen in terms of reagents aren't necessarily clear in retrospect. All right, so your active catalyst is actually still palladium 0, and this is a 10 electron, D10, 14 electron complex. 10 d electrons and then 4 electrons from ligands. Okay, so the first step of this reaction with this as our active catalyst is basically going to be oxidative addition of the aryl halide like we saw before. So here's your aryl halide in the reaction we just listed. And the oxidative addition step is basically going to involve lone pairs, a pair of electrons from palladium making a bond with carbon, and then the bromine. Oops, sorry. and then the bromine attacking the palladium. This is going to give us a new complex wherein 4 things are attached to palladium, including our benzene ring and the halide. The charge on the complex hasn't changed. It's still 0. You've got 2 X-type ligands, so in order for the charge to be 0, palladium has to be in the +2 oxidation state. It's now a D8 metal, and this is a 16 electron complex. Again, the fact that it's a 14 electron complex versus 16 just reflects the fact that there's space for more things to happen, right? If this were an 18 electron complex, there wouldn't be space around the metal for oxidative addition. The fact that it's still a 16 electron complex here means that there's space for more things to happen. All right, so that's the oxidative addition step. All right, the next step is called ligand binding. We've, as I said, in a 16 electron complex, we have space for another ligand. So the pi electrons from that olefin are going to sit down on and coordinate the metal. And I don't have a really great way of drawing that other than with the dotted line like we talked about previously. This is still a charge 0 complex, so it's still palladium 2. Only now, and it's still a D8 electron complex, but now it's got 18 electrons total. That means it's coordinatively saturated. There's no more room for other things to bind. All right. Question so far: oxidative addition, ligand binding or association to give you that complex. Yeah.
So the coordinating here, it's not a bond, but it still counts as the electrons?
It's a bond in the same way that either all of these are bonds. It's just the pi electrons are involved in that bond.
Oh, gotcha, okay.
Yeah. Kind of hard to show with anything other than drawing the pi electrons really close to the complex. So the dotted line is just indicates that it's the pi electrons that are binding. Pi electrons of the olefin bind to the metal. Okay, what happens next is a new step that you're not, that you haven't seen before, and this is really the only time that you'll see it. It's called migratory insertion. And this is the carbon-carbon bond forming step. So what will happen is the Sp2 carbon of your original aryl halide, the one that's bonded to the metal, is going to get transferred to and make a bond to the Sp2 hybridized carbon of your olefin. And at the same time, electrons from that pi bond are going to attack the metal to make a sigma bond between the other carbon of the olefin and the metal. So I'm showing you in 2 different colors sort of the 2 new bonds that are forming. All right, let's draw what that looks like afterwards. A new thing that's bonded to the metal is the blue carbon of the olefin. At this stage, if you want, we can draw in the hydrogens that are implied but not shown. I don't know if that's helpful or not. Let's just leave them out. And then here, oops. Sorry. Dang, I think I'm missing a carbon, aren't I? No? I'm confused. Okay, well, can I undo all the undoing? All right, yeah. All right, so here's the new bond we made between the two what used to be sp2 hybridized carbon of the olefin and sp2 on our aryl group. Yeah.
This might be a little late in the class period, but are you?
I am recording, yes. I did press record. It's a good bet, though, to guess that I wouldn't have. So thank you for watching out for everybody. Yeah, if you assume that I've forgotten something, that's usually a safe assumption. All right, migratory insertion. Let's check our oxidation state. We still have two X-type ligands attached to the metal. The overall charge on the complex is still 0, so this is still palladium 2. Let's count d electrons. Because it's palladium 2, that's a d8 complex. However, we've gone from something that was 18 electrons complex to something that's only 16. 8 plus 2, 4, 6, and 8. So that migratory insertion step got rid of that extra pi ligand, so now we're no longer coordinatively saturated. All right. What I want to show you here is the basis for the stereochemistry no, I'm not, man. Okay, the stereochemistry of I told you that we would preferentially get trans stereochemistry about this double bond that was originally involved in the olefin. All right, so before the next step can happen, we actually have to rotate around this carbon-carbon bond such that a hydrogen is pointing towards the metal and not this aryl group. So I'm just going to redraw our complex in sort of the same way, only I'm going to put a hydrogen here. And though I didn't show stereochemistry of the Z group, the most, and I'm only showing you one of the possible orientations, the most stable conformation of this intermediate is the one where the large aryl group is opposite the Z group. Okay. Now, with the hydrogen pointed towards the metal, we can do a new mechanistic step, again, that you're only going to see here. It's called beta hydride elimination. And basically, this involves electrons leaving the metal, collapsing to form the pi bond at the same time as hydride leaves and gets delivered to the metal. So the hydride gets eliminated and goes back on the metal. Notice that this is the stage at which we release our product. And if you pay attention to the relationship between these two groups in this more stable conformation, that explains why the new double bond that we made is trans. Ooh, run out of space. Okay. After that beta hydride elimination, we're still palladium 2. Only now we've got H and Br attached to the palladium. We need basically a reductive elimination step. And this is where the base comes in. The triethylamine base deprotonates the metal. Electrons come back onto the metal, and then Br minus leaves. We get out of that the protonated conjugate acid of our base and Br minus, and then that takes us back to our palladium 0 species. So that's the catalytic cycle. This one's way more complicated than the Suzuki, because not only do you have oxidative addition and reductive elimination, but you've got a lot of other things: ligand binding, migratory insertion, beta hydride elimination, and then reductive elimination to give you your overall complex. Now, why did I show you all of that? Basically, what are you responsible for? I just want you to know the reagents and to know how to predict products of the Suzuki and Heck reactions. By the way, pay attention to this. One of the potential products of a Suzuki reaction is a diene. That can do Diels-Alder reactions, so maybe you want to go back and look at that. All I want you to be able to do is to predict the products of a Suzuki and a Heck reaction and to use them in a synthesis. I'm not really going to ask you questions about mechanism for those two reactions. I am going to ask you questions to assign oxidation state and d-electron count of metals, because I want you to be aware of that. And you know, for a lot of you, this kind of thing, you're not going to encounter these things too much in your future. But if you decide you're interested and you want to know more and you end up going to work for Professor Michaelis or Professor Castle, these are kinds of things that you'll encounter and be familiar with. All right, last reaction. Wait, questions on the Heck? What the heck? The Heck reaction. Okay, the last one we're going to do is called olefin metathesis. Your study guide says something about carbines and cyclopropanation. That's fun and interesting, but we're going to skip it. So the last is just olefin metathesis. And this is a Nobel Prize winning reaction for the 3 chemists that were involved in its discovery. And we'll focus in on one of them, Professor Bob Grubbs from Caltech, and I'll show you his catalyst. Metathesis is a reaction that involves connecting or cross-linking or trading groups. So let me give you an overview of this process. We here have alkene 1. This is called a terminal olefin because it's got a CH2 group on one side. And then maybe alkene 2, which is also a terminal olefin. Metathesis is going to involve a catalyst the two terminal carbons are going to end up attached to each other to give you ethylene. And then the two internal carbons are going to end up attached to each other to give you this other product. This is going to be called cross metathesis. Because you've taken two different molecules and you've attached the two blue carbons together. This is not a self product, but a cross metathesis product. Of course, you would be worried about the formation of both the cross metathesis product and the potential self metathesis product. Maybe for fun, I should color the other carbon, I don't know, maybe pink, so that the distinction between self and cross products are clear. You could have a cross metathesis product, you could have this self metathesis product, and then you could have this other self metathesis product. Okay, so obviously that kind of thing looks a little bit messy, and it is. So we're going to try to do reactions under conditions where we can control for this. I'm also going to point out that this reaction is an equilibrium reaction, and the choice of terminal olefins is deliberate, because one of the products we're going to make from this reaction is ethylene, which is a gas and which rapidly gets removed from the equilibrium by bubbling off. And so by Le Chatelier's principle, you can push the reaction to completion. All right. So basically what we're doing, again, this is kind of Lego chemistry. You're popping off the terminal olefin groups, hooking them together, and then clicking together the internal carbons. And you don't have a lot of control, at least as I've set this reaction up, as to whether you click blue to blue, pink to pink, or pink to blue. So we're going to need to arrange the situation where we can have a bit more control. One of the places where you have quite a bit of control is if the reaction can proceed in an intramolecular fashion. So I'm going to draw a molecule that contains two olefins. Okay. It's got the terminal Ch2 groups, which we're going to color yellow. And then it's got these internal carbons involved in the olefin. Now, if I use this catalyst, and I'll draw what the catalyst is in a little bit, I can form, there'll be a driving force to, again, click off those two terminal Ch2 groups and then click them together to make ethylene. And then presumably I could, there's a lot of things that could happen, but notice that the pink carbon is 5 bonds away from the blue carbon. And if we make a new bond between blue carbon and pink carbon, that's the favored metathesis product. This is called ring closing metathesis, or RCM. and 1, 2, 3, 4, 5, 6, and that's going to be more stable and faster to form than any of the other products you could imagine. For a molecule that has two alkenes, you could imagine, well, why don't I just start clicking one alkene onto another, and make polymers? That's actually a possibility too, but in this case, the ring that we form is a 6-membered ring, isn't very highly strained, and so there's this driving force to just have the ring close rather than to do anything else. Okay, questions about the overview of metathesis and what we're doing? Okay, yeah.
Is our trans products preferred or?
Are trans products preferred over cis? That probably depends on whether you're forming a ring or not. It's an equilibrium process, so I would think that trans would be favored, but you can't get a trans double bond in a 6-membered ring. And you might expect to see a mixture of the two depending on context. Yeah. Now let's see. We could spend a ton of time talking about mechanism. But I'm really not going to ask you a question about mechanism. So I probably will leave that to it should be in your text, and if you want to know more, you can look at it. I want to show you what the catalyst is. I think you probably better recognize the catalyst so you know to use it in a predict products or provide reagents sense. This is one of the catalysts produced by Professor Grubbs's group. There are multiple generations. This is one of them. As with the Heck reaction, the thing you put in the reaction mixture is sort of a pre-catalyst. You've got chlorine ligands. You've got a phosphine ligand. It turns out the R groups here are cyclohexane rings instead of benzene rings. Presumably they tried a bunch of stuff and that's what worked. And then this one's weird. It's a doubly bonded ligand. This is an X-type ligand, only it's an X. Well, I'm not sure I understand that well enough to even say anything about it. So I'm not going to ask you to assign oxidation state or d-electron count for this ruthenium complex. I think looking at it, let's see, ruthenium normally has 8 electrons. The complex is neutral. Yeah, I'm not even going to worry about oxidation state or mechanism for the Grubbs catalyst. The mechanism is interesting, and if you go through it once, you'll get a sense for really what's going on. I guess I'd rather talk about some potential applications of this reaction, that we've done some things in my own research. So, but before we do that, let's do a predict products question. Or perhaps a retrosynthesis question. Suppose I want to do this by an intramolecular ring closing metathesis reaction. RCM stands for ring closing metathesis. How do you show what the starting material would have been? Take the 2 carbons that are involved in the double bond, The metathesis reaction would have clicked those together. Immediately prior to the reaction, however, each of those two carbons would have been bonded not to each other, but to a terminal CH2 group. So one thing to pay attention to when you're doing metathesis reactions, especially ring closing metathesis, you lose two carbons, right? The other partner, which we weren't thinking about as we looked at our product, is ethylene, which bubbles away. So those two carbons go missing. So when you propose a starting material for a ring closing metathesis product, you have to remember to put in those terminal olefin groups. Okay. Now, this reaction has been used all over the place in peptide and protein chemistry. I'll show you something that we've done. We were not even kind of the first to do this, though we've tried to understand its impact for how a protein folds. So we work in my lab on a protein called WW because it has two key tryptophan residues in it. And I'm not going to draw the structure of the protein for you other than to say it's this triple-stranded anti-parallel beta sheet. So we'll use this arrow to indicate one beta strand. There's a turn, and then there's another beta strand here. The two beta strands are hydrogen bound to each other, so we could put dotted lines to indicate hydrogen bonding. And then there's a third smaller beta strand here, which is also hydrogen bound here. Okay? That's the general structure of this protein that we're interested in. Oh, yikes. Interested in. I could show you the structure, but this is good enough. And we've studied this protein enough that you can do an experiment called circular dichroism where you can tell whether or not the protein actually has that shape. It's an experiment where you shine polarized light on a molecule, and it's kind of related to like chiral, the fact that chiral molecules rotate plane polarized light. Anyway, we have a signal that tells us whether or not this protein is folded. And we can tell how stable the protein is by increasing temperature from really sort of almost freezing to almost boiling, and then watch this signal of foldedness, and you'll generally get something that looks like this. Maybe this is 100% folded, and then at some temperature the foldedness will start to go away, and then you'll get to 0% folded, and that signal tells us something. We can fit those data and we can get numbers out of it. For example, the spot where the protein is 50% folded, we call that the TM, or the melting temperature, and that's a qualitative measure for how stable the protein is. If you have to turn up the temperature hotter before the structure goes away, the protein must be more stable. And we can actually turn that number into a free energy to try to understand how stable a protein is. Now, for various reasons, one of my students asked the question, if we attached something unnatural to an amino acid side chain, and suppose the thing that we attached had a terminal olefin. All of this stuff, these oxygens and these two alternating pattern of oxygens and two carbons, oxygens and two carbons, that's a flexible linker that we've used for a lot of purposes. My student asked, what if we take two of these. And we put them at locations. This was position 16 in the protein. This was position 32. What if we put them at locations that are far apart in sequence, but are close in the folded tertiary structure of the molecule? And then what if we use the Grubbs catalyst to do ring closing metathesis? All right, so what would ring closing metathesis do? That should clip off the terminal group, and that should clip blue to pink, right? So, actually, I'm just going to put that here and paste that here. So the ethylene, oops, yikes, the terminal carbons go away. And it's these two that get bonded to each other. I'm going to have to sort of slide things over and that's terrible. Oh well. I can't tell at this point whether I've lost atoms or not, but sort of mostly good. Close enough. Okay. So now these two positions that are far apart in sequence are now constrained to be close to each other. And we repeated the experiment where we assess foldedness after doing this reaction. And it turns out that you had to turn up the temperature to a higher amount before foldedness went away. So, oops, it's smoother than that. Anyway, you see a shift in melting temperature from here to here, and that happens because of the ring closing metathesis reaction. And the explanation is presumably that by connecting two positions and forcing them to be close to each other, you pay for some of the entropy cost for folding the molecule into this shape. We've gone on to do some things where we're like, okay, well, does it matter where the crosslinks are? If I move this position over one or move it this way, does it matter? If I change the length of the linker between the positions, does that matter? Can I do this in other types of proteins? What we'd really like to know is if given a protein structure, could you look at it and decide in advance where the best positions to staple the molecule would be? Why you would want to do this in the first place is a couple of reasons. First, suppose having this particular shape is important to bind something or for enzymatic activity. If you make the shape more stable, you might just make enzymatic activity or binding affinity better. And there's tons of examples of this from groups all over the place developing inhibitors of various biological processes using molecules that are cross-linked in sort of this way. Another reason you'd want to do this is suppose you want to use this molecule, and what I've shown you here is just a model system. This molecule basically isn't very good for much at all other than to make these measurements. But suppose you had a molecule like this that was useful as a drug and you wanted to administer it biologically. Your body has all types of ways of getting rid of protein. For example, we eat meat, so our guts digest protein. This is why if you take insulin because of diabetes, you don't take an insulin pill, you got to inject it, right? So a lot of these protein drugs end up needing to be administered by injection. Even in your blood, there are proteases that can chew a protein apart. We and others have shown that if you make a protein more stable, the red protein gets chewed apart less quickly, more slowly than the blue, less stable protein. And so having strategies for generally making a protein more stable this way could make more useful drugs. So anyway, that being said, this reaction, it's a Nobel Prize winning reaction. It works great in organic solvent. It doesn't work too well for proteins, at least not in our hands. In order to get this to work, we had to do this actually while the peptide was still bound to resin. And instead of using a catalytic amount, we had to use a 40-fold excess of the Grubbs catalyst, at which point it is no longer a catalyst, but a reagent, and a very expensive reagent that you're spending, having in vast excess. So the development of reactions that can cross-link two groups in aqueous solution without any protecting groups is an active and important area of chemistry, and it's something that people are working on. So that is it.